Okay, yeah, sorry that for the delay. So really, I will get started. So we're going to talk about, last time we talked about some image recognition. This is not IT, right? I guess I should be able to load this.
Hello, I missed a call from this number, and I was just calling to check see.
Okay. So we're going to talk about detection today. So in particular, we will talk about a pretty famous detection technique called Dalal Triggs, and also like deformable part model. So let's just look at the detection problem, just an overview for detection problem. So unlike the recognition problem, we want to have an image. We're trying to find something in the image, right? Let's say we want to find whatever, a dog here. And of course, the detection problem is much more complicated than a recognition problem in the sense that like, you may have many different objects inside the image. Then you want to detect all of them, and they can have lots of variations like illumination and occlusion and so on and so forth. And this is just a general a general process like to do a object recognition, actually object detection, I say. So first of all, like you need to specify the model. So model-wise, for example, like we did HOG before, like we can have like HOG features as the model, or like we can have like part model like for detecting different parts and then trying to link them together. And a specific case like we can combine them, like for example we can have like a hybrid model that with template detecting like individual parts and then trying to combine them together with part models. And we can also get into more complicated model like 3D models, and to trying to like look kind of detect like each of the parts and then like trying to like understand what's the objects like indeed 3D and trying to kind of match that. And we can also have like deformable part 3D model. This is for example like this one here.
Shapes from approximately 4,000 body scans.
Probably, this will work here. Just at the top.
Use principal component analysis to estimate the directions of maximum shape variation. These are our shape blend shapes. Here, we show the first few principal components of the male and female body shape. The shape blend shapes are linearly combined and weighed by the shape coefficient of beta. The result is offsets that, when added to the base template, give a new body shape. The joint locations are predicted from this body shape. All the blend shapes are simply displacements from the template, and, once summed, to produce a deformed body shape. The skinning equation is then applied. Symbol allows the independent modification of pose and shape. This is similar to previous models like skin, which are based on triangle deformations. Symbol.
Simple, I guess. I'm not sure about that. But what I mean is so it looks like you can have lots of different models trying to match what you have like as features. So a question may be like, maybe how about just pick the most complex model? But the problem, of course, is complexity, like influence will be harder to fit, and you may want your application to be real time, and so like you may not be able to afford those models. So, and then after you have the model like features matching like what you want, and then you try to make some hypothesis. Some simple case may be like you have an image, you just have a sliding window there, like try to just lie over like and fit with your model. Another, of course, because you don't know what scale like your object is supposed to be, you may need to try different scales. So you may need to zoom into different scale and try it again. So wow, I don't know. So that's another possibility is that we can also like instead of like scanning for the entire image, you can just like look into several key points like and just capture like patches like I'm trying to detect from there. And also we can look for some so-called region-based proposal. So this is like some of these old algorithms like in computer vision, like you can just have some able to extract some boxes, basically saying in this case it's actually even a particular region, saying it's likely in this image that part is correspond to something looks like an object. So and with that, and then you're trying to detect features as we described earlier. And then like, we can do scoring for those hypotheses, and then like we solve some detection problems. So some of this simple trick here is, for example, like we have we can apply a non-maximal suppression as a post-processing step. For example, to look for some objects, like for example a face here, and then you find two boxes like both correspond to some face, and then you apparently they not supposed to be overlap like two faces. So then most likely it's just duplication. So we're trying to suppress those duplications. Another like simple trick is like just use context and reasoning. For example, if we were trying to do some pedestrian detection, then we know that the people will most likely not climbing the building, so will not be above like certain points there. So we can put a limit and saying that we detect anything above that is not a people or something, not a person. And and how do we evaluate our algorithm? So we need to. I'm not sure how you guys are familiar with this. Like it's simple. I mean, it's some fundamental machine learning idea. So you, of course, you have some prediction and you have some ground truth here. Let's say I have an image here. You have two people here are the ground truth. Like you know they are the actual pedestrian here. And then I have this detection result that this apparently miss it and this miss it, and I have this mostly correct. So to evaluate that, like we should count the true positive and true negative, right? So or like true positive and false positive. So in this case, for example, we can give a rule here saying that like whatever we detect the region is more than like 50% overlap with the ground truth, you say like we able to detect the person. So then in this case, like this one will be counted as a true positive, and this two will be not. And then like so this will be like the false positive, right? So the algorithm thought that this is a person, but it's not actually a person, so it's a false positive. And we also have false negative here. So basically, you have a woman here. We are not able to detect it. So by the way, what's the true negative here? So anyone can wake up now like true negative? Like what? Any example of true negative here?
I'm sure the sky up there.
This one?
It's a little bit
Yeah,
hard.
all of the background is true negative.
It's
Yes.
a little bit hard to tell the color for prediction from ground truth.
So this the green box here is the prediction, and the yellow is the ground truth. Yeah, it's written here. So and then like you can build a confusion matrix kind of like or confusion matrix table or like and then like you can just tally that like the number of true positive and true negative, false positive, and so on. And there's other names for that, like for example, like true positive, sometimes we call it hits, and then like false negative we call misses, and then like false positive we say false alarm, and so on. And then like this is the precision recall, like so the precision basically is the true positive over like all the detection there, like or number of like or the, so basically you say like it's 100% precision, and saying that like everything you detect is really that object, really a true object there. And the recall is the true positive over the true positive plus false negative. So basically the recall is like, if you have 100% recall, it's like everything in the image is pedestrian necessarily trying to detect people, we are able to detect those. So of course there's a trade-off here. You can set some threshold saying like, I want to have more. Okay, let's say this is an example here. So for example, like we have an algorithm here, we set some threshold, and we this is like, again, like this is the people here, right? Yes.
Is precision the same as probability of detection?
No. Yes. No. Yeah. It's probability. You will say, yeah. So you can say that like empirical probability. Yeah. So but you need to be careful. That's different from like, for example, accuracy. Yeah. Accuracy you can't like, yeah. So and then as I said, like here that you can have some trade-off, right? Let's say you start with an algorithm, like you set some threshold here, and say like these are the people, but you detect these 3 boxes here, right? So in this case, what is the precision, by the way?
Not 100%.
Yeah, but how much?
90
No.
of just the guy.
Yeah. Okay. Look at this image again.
Yeah.
This is the prediction result. Like.
You mean the precision overall?
Okay. Go back to here. This definition of precision and recall. It's good to understand this because this is very common idea. So it's like in machine learning. So it's not just machine learning, like in statistics also. So precision is basically how much you detect is actually correct. So like you have like lots of results coming back, but not everything is correct. So therefore, in this case, like you have detect 3 boxes here, right? But only one of these is correct. So therefore, like the precision is 1/3, or like 33% about. And so how about recall? So if you look back to the definition again, like, so recall is meaning like how much you can actually, yeah, how much?
1/2?
Yes, recall will be 1/2. Right? You have 2 of them are people in the image, but you can only catch 1 of those. But know that like I can set the threshold, right? Apparently I have some kind of threshold. Maybe I can make it harder to say, like, let's say after I have some go for my algorithm, machine learning algorithm, it should give me some score. Right? Basically, if the score is bigger than something I said, like it's a hit. So now I can reduce this threshold, or like increase this threshold to reduce the number of hits, right? So, and for example, like this one, I reduce the threshold quite a bit, so I have lots of hits here. Now, in this case, what's the recall? Recall is perfect now because like you have both of these people is able to be detected, but the precision is quite bad. Like you have like 2/7, right? You have like I don't know what is 2/7, but the precision is pretty low. But now you can increase the threshold, right, to make the detector like output like less number of detection. Less number of hits. So then in this case, like the recall reduced like to 50%, but the precision increased. So in general, you can always trade off that. Then you have this called a RC curve. Like what's that stand for? Anyone remember RC curves?
Again?
ROC curve.
Region of divergence?
No. Nielsen may know that. ROC curve. receiver operation, something like that.
Characteristics.
Huh?
Characteristics.
No, actually not. I think it's receiver operation. So it's something like very old idea in statistics.
Yeah, receiver.
Operation curve, something like that. But it's people commonly just call it RC curve. So it's just a trade-off curve of your recall and precision. So you can make recall bigger or like precision bigger. So of course, ideally, you have this RC curve like want to occupy this entire like cube here. Square here. So then in this case, you will have 100% recall and 100% precision. And so you can compare different algorithms, maybe like just look into like what's the area underneath this RC curve. So if like this area is bigger, then you say the algorithm is better. For example, here there's a comparison of 3 different detection algorithms here. So this one is DPM and HOG. HOG is basically the Dalal Triggs. I'm not sure how to pronounce the Indian name there. So, but anyway, these are the 2 algorithms we'll talk about today, and there's some very kind of like much better algorithm that's like based on deep learning. Maybe we'll briefly go over that like a couple lectures later on. So and then like for example like this case, then it's hard to say. Apparently this one you can easily say, okay, this is definitely better than this. But if you have RC curves like this, I guess it's still this is better, but it's not so apparent. Any questions here? So and I just want to give a quick not a review, but like I think this is a nice one-page slide. I guess I got it from, I forgot, it's from Stanford or like from Brown's, Brown's. So here you can see some of this pretty influential result in detection. These are the tools I'm going to talk about here, the Dalal Triggs in 2005, and also like the DPM, like deformable part model. Like they have a journal paper in 2010 also. And we will also like talk about Viola Jones, like maybe next time. And so first look at this Dalal Triggs detection. So maybe I get you guys interested. Let me just show you a nice, a simple demo for that first. Maybe. Let's see if I can still remember where is it. Yeah, it's here. I need to. So this is like some this is like a pedestrian detector using Dalal Triggs. So you have this image. I have a couple images. Let's say this first image trying to detect pedestrian, detect people, and I have another one like this. And this also like apply non-maximum suppression. So okay, it doesn't look much difference because like these 2 boxes is quite nice. They do not have much overlap. And this some more results here. I think there's some okay, like this one. There's some basically like incorrect detection here. But if you add, add the non-maximum suppression as a post-processing step, you can eliminate this result here. This incorrect result here. So there's a couple. It's okay. It's not too bad and too good, but it's doing a pretty decent job. And actually, it was like state of the art, like just I would say 7-8 years ago. So just like things just. So it's like pretty nice. And in terms of speeds, it's quite fast also. Let's see, I think I even have a I forgot where yeah, I put it here. So let's see. I may need to again okay. Of course, I didn't detect anything, and it's difficult because it's for my laptop webcam, and there's no people here. I can pretend myself as the pedestrian, see if it's working. Yeah, okay. So I check myself like this. So so it's like kind of real time. Like you see, like it's what's spectacle, and my laptop is like several years old. Like I don't know how like 5 years old. And one thing, I think i5 like pretty slow CPU and doesn't have a GPU. You know, like Lenovo always have like bad laptop with integrated. I mean the laptop is nice. I mean robust, but in terms of graphic cards, it's pretty bad. So it doesn't use any GPUs and it's running kind of okay. So I guess I have my laptop. Okay. So that's the Dalal Triggs. So I mean, like if you want to use this as a project, it's very easy. And if you look at the source code, like it's actually if you just use OpenCV, it's just actually just one line because like it's already okay. Spider, it's not coming up. Let's just use gedit. So I'm not sure you can see clearly if I need to increase the font size, but maybe I can. Let's see. I always have a problem with that. So anyway, I give up. I assume that you guys have good eyesight. So, but you don't need to look into that anyway. So what I want to say, like, if you use OpenCV, it's just one line of code basically. You just have a default Dalal Triggs pedestrian detector already implemented there. So you just like load the descriptor there, and then like when you detect it, just use the detector. Then it will give you the rectangle. That's the detection. And also in the image utilities, you can find the long maximum suppression algorithm is also implemented, so it's also one line of code. So of course, like this is not state of the art though. So but it's like if you want to do some simple project, it's already in OpenCV basically. So let's talk about the algorithm itself. The algorithm is based on HOG. By this time, I guess you guys are quite familiar with that because of the homework. So basically, what it does is like this is the overview for that. So it look into like a fixed size model here. So of course, like your people will look bigger or smaller, but it doesn't matter because you can scale the image into different scale, right? So it always look into assume the people, the person size is like 64 by 128 pixels. Then compute the HOG, and then it basically score using SVM and so on. And then you can optionally like do some maximum suppression as I just show you. So this is a little bit more detail. So basically it partitioned the this is what the size again 64 by 128 into like 4 by 8 cells here, and then like some pre-processing step you can do some color. Okay, you typically you can change to other color space the RGB is sufficient basically, and then like you can do grammar correction also, like basically just scale the intensity a little bit. It gives you very slightly improve in performance. And then, like, of course, to compute HOG, you need to first compute the gradient, right? So you compute the gradient image, and then afterward, like you compute the HOG. In that case, like they use a unsigned HOG. So like, in the sense like the angle is not from 0 to 360 degree, but just 0 to 180. So and then like it has basically 9 different bins there, and rows by magnitude, as what you guys did in the homework also. And they use bilinear projection in the sense that if you have 2 cells, for example, like if your result is 85 degrees, then you split is the word. Split the weight like one quarter to 75 degrees bins, and then 3/4 to 90 degree bins. So does it make sense?
We just a linear or
It's just a linear, yeah, linearly. So yeah, so because 85 is closest to 90, right? So therefore, yeah, it's one-fourth closer. So then afterward, something is interesting, like how they implement that. They try some experiment. They find that they need to do some normalization because like the intensity change. Like you have like image from different intensity. If you don't do normalization, the performance will be much worse. So how did they do normalization? Is basically you have the cell and you look into labeling box, labeling cells. So for example here, it will basically look into these 4 different cells here, and then you normalize, like assuming like all of them together, and you normalize it by this one. So normalize is basically just normalizing to 1. So you have some E here. It's a very small number just to avoid like some numerical problem. And then like you repeat that like 4 times because you have like 4 labeling combinations, right? And then like afterward, like you basically, it seems a little bit weird to me. This normalization, you will cascade all these normalization features together into one big features. So it seems to me that there should be some redundancy here, but it doesn't matter. It just work well. And then like afterward, just use SVM. So support vector machine. You guys know support vector machine, right? But anyway, it's like now it's basically it's like some black box now. You can find toolbox very easily everywhere. Just call it and you can train it and get the classifier for that. So and then like after you basically like support vector machine is just a linear classifier. So it's the support vector in the sense like, for example, you have 2. It's like this is the feature space, let's say, and this this is one class result. This is another class. So then you want to find the best like linear separator for these 2 different classes, right? So then how do support vector machine does is like we most likely we should ignore all those data points that is like far away or like from the boundary there, like this here. So we just care about the one is like close to the boundary. Well, here what I mean is like, yeah, I didn't give a good close to like the boundary between these 2 classes. So then these are called the support vector basically. So then you just draw a line in the middle of that. So there's some nice mathematics behind that, but yeah, but I won't spend time here. So then afterward, you train this support vector machine, and then like you can do the detection. So you have, let's say this is your features here, then this is W and B are the train weight, and then you compute the result, and they say is bigger than 1, so therefore it's a pedestrian, it's a people. So this is kind of a summary. Oh, yeah, I guess I will just skip that. That's the same thing anyway. the initial paper, basically, they used the in-real pedestrian database. It's pretty old database now because this work is back in 2005, right? So now there's better database, like for example, ImageNet and Coco and so on. That's the. Yeah, I will just skip this one. So this is some of the results, but I guess I won't spend time on this also. Anyway, like this is not the best, but as I said, like this is something you can get your hand dirty very quickly if you use OpenCV. If you have some pedestrian detection application you think of, then everything is already there. So 3 lines of code, you are done. But as I said, it's not the state of the art. If you want to look for something more sophisticated, you need to look for like YOLO or something like that. So it works. Actually, this kind of algorithms is all in the category of sliding window detector. They work quite. Yeah, I forgot. Okay, it work well. Like because it's assumed basically it's a template matching, right? So if the object doesn't deform too much, it works quite well. So therefore, like if you're a pedestrian, typically they are walking, it's quite reasonable, like the shape there. But if it is pretty bad if you're trying to like, for example, detect cats and dogs, they are more creative of their gesture or whatever. I don't know. So the string and releases, I won't spend time on that, but apparently it's very fast, yeah.
How suitable is it for cases like the previous homework where we were doing transforms on the image? Template matching? Can it do the same kind of affine transform template matching?
You can theoretically, but then like you don't have the latter part. Let's say, I mean like you're not going to use the SVM so on, right? So you only pull out the feature extraction part basically. Mm-hmm. So maybe, but that is basically very similar to the original HOG. Then the only difference is like they do this normalization step. But I don't know. I didn't try it myself. At least like for us, like if you did the homework, even you ignore the normalization, it worked pretty well. So therefore, we can ignore that for that particular application. Yeah. So, but of course, if you do the normalization, it may be better. But then you just spend more time on computation. Yeah. And another weakness is besides is not suitable for highly deformable objects. It is not robust to occlusion. But what can you say? Because if you detect, object in image, of course there's very nowadays. For example, you have a mass RCN and it's doing something really amazing. Like even you have partially occluded, it did pretty well, but. For this more conventional algorithm, like you really cannot expect much, and also like you require a lot of training. But of course, like nowadays all algorithms require lots of training data. And this is for the Dalal Triggs algorithm, and I would like to talk about something a little bit more sophisticated than this one. So DPM is the deformable path model. It's basically like the state of the art deep learning, basically. That's the best detection algorithm before people using deep learning algorithms. And it's introduced like 2008, something like, and I guess the journal paper is 2010. So the idea is very simple. As last time we mentioned that you can detect something using bed of words, right? But of course, it's bed of words is good for recognition. Just what kind of scene, for example, you have an image. You want to know like what kind of image is that is doing pretty good job. But if you want to detect individual objects, then bed of words is pretty bad. So, but deformable path model is just an extension of this idea. So you split into all these components. You can think of like also words, right, or like paths in this case, and then you just link them together. So you expect, for example, I want to detect a face. I would expect eyes are here, nose is here, like mouth is here, and so on. and then like that's what you expect, and then like therefore like the model itself, like the part models itself is quite general, so it didn't say like what kind of like individual detector you use. Even though like typically people just use HOG or like the Dalal Triggs detector for detecting individual parts, and then they try to combine them to get more accurate detection. And then this is just an example, like you have a people here. If you have a person again, if I try to do a pedestrian detection again, I'm trying to detect the whole body first, like that would be a wood detector. That is basically is the same detector as what we saw like in Dalal Triggs that is in the demo. So then you try to also train your detector to detect like individual parts, like for example the head, the arms, the legs, and so on. And then you're trying to link them together. And yeah, that's basically it. So this is an example of this head detector, and also like this the whole body detector here. Oh yeah, that's exactly what we saw. The HOG way for the Dalal Triggs here. That's the filter there. So then you can also detect other things, right? For example, you can detect bicycle. In that case, you have one big, let's say, wood detector for the entire bicycle, trained to be learn to recognize this. And then you also look into individual parts, wheels and legs, and so on. And of course, like here, like frontal detector will be very different from the side detector, because you expect like this is just looks totally different. So basically, they are actually detecting two different things here. So that's frontal view and then like the side views here. So that's again like just more like model here. You can also like car models, let's say. So now look into more detail. So basically you have a filter, let's say the wood filter F here, and find pH here is basically the HOG. So his is just represent concatenating like all the HOG features, like for different scales. And then the entire things will go through a filter, and you are supposed to train this filter. And then therefore the model will compose of the wood filter, and then you have individual parts. Individual parts will basically compose of individual parts filters, and then you have some anchor position is basically where you expect by default, like your expect position of your arm or your legs if you are detecting detecting a person. And then like you have a deformable cost function trying to compute like if you have basically it's like a transform. So if with the part model like from the HOG features, you're trying to like take into account like both the HOG features and the location of that expect or like the computed location relative to the wood filter, the wood location there. And okay, let's look at let's look at this here maybe. So this is the more precise the map here. So this basically the entire score is like this. So you have this is basically the entire score is composed of like the individual part filters score and also like the wood filter score. Wood filter score will correspond to I equal to 0 there, and subtract with like the deformable cost, deformation cost. Basically is the DI there that we described earlier. I think my slide here is not the latest one. I think I correct this subscript here. Anyway, so and this is and this DI will basically take the distance, the detected distance for x component and y component, and also the square of the distance, square of the components as arguments. and this is the overall pipeline here. And as you can, maybe like we can get into more detail here. So you basically, you have an image coming in where you compute the HOG features like for the entire image. Then you look for the, just like in the Dalal Triggs, trying to look for, using the wood filter, look for the people there. Then afterward, like when you find some, okay, and also like you're trying to like also apply the path filter like to the same HOG feature also. So then in this case, you basically have response for the wood filter and response for the path filter. So the peak here will correspond some potential hits for the people there, right? So then you want to combine this like wood filter and path filters information together. Then that's basically you use like this prior knowledge that you expect, like if you have a body here, the head is probably here, won't be like at the back, but or something like that. Then you, with that, you basically you have a response of okay, with this path filter response here, we go for this kind of DI transform. So basically, so it's a little bit black box here, but then it will give you like the expected maximum for the path there. So if like of course if that path is located, or I should say like if the path is located in the right position as you expected from the wood filter, then you will have a more it will have a larger intensity here. So otherwise, like if you, this is like far away of what you expected in the supposedly the true location there, then it will be smaller. Then you will basically combine all this together, right? So then you will have a this combined result. Then you can look for the peak and find the detection. And that's basically it's just more example here. So I mean like DPM is just a summary here. Basically like as you can see, it's a pretty generic approach. So you can use any kind of filters like to start with, or like any kind of feature detector to start with DPM, even though it's common to use HOG. And then like you can basically like you just combine all these models, I mean path model and also the wood models together, and take into account of the relative position of all these locations or supposing location. And then advantage is like it's pretty intuitive and it's pretty generic. You can not just use it combined with like HOG, you can combine with other detection method also. It works well with like lots of categories, but of course like it's kind of like tedious, like, because like for every new kind of categories you want to detect, you need to design something manually. Basically, for example, like if you want to detect people, detect person, you expect like the head is there, like arm is there, or something like that. At least you can't expect like what kind of components you're supposed to have. And sometimes also like there's no guarantee. Sometimes some components may be missing. For example, like if there's occlusion, maybe the legs is disappear and the arm is disappear. That will affect your detection result. And of course, when you want to switch to another category, you just need to rebuild everything. So so. But in any case, as I mentioned, it's basically it was the state of the art like just several years ago, and there's some potential modification or improvement. Let's say instead of like doing a star shape model, maybe one can do a fully connected shape model. So but anyway, that's basically what we have today. I am